All right, thanks to the organizers and to everyone who came out in the middle of August for this set of talks. I'm going to talk about investigating the hypothesis of magma-assisted rifting. And I want to acknowledge the team who's working on this under an ERC grant, and in particular, Yuan Li, who is the sort of lead architect of the calculations that I'll show at the end of the talk. But Adina and Dave have been instrumental, and Han Wen is a PhD student involved. And I want to say thanks to Dave Ferguson and Ian Bastow for introducing me to the literature on rifting. I want to advance slides. Here we go. So here are some candidate forces for continental rifting. And of course, there's always subduction. Slab pull is a strong tectonic force, but uplift and gradients in gravitational potential energy, as well as basal tractions, may also be relevant. And we know that since the 40 years that subduction is the strongest force in plate tectonic force balances, and that it can produce forces greater than about 15 teranewtons per meter, and that was really reinforced by this study that Sasha was involved in, where rifting was modeled in a plate that was connected to a subduction zone, and the stresses that built up prior to rifting were hundreds of MPa, consistent with forces greater than 15 times 10 to the 12 Newton per meter, or 15 teranewtons. So these are very large stresses, and it's not hard to imagine that this can rift continents. But what about gravitational potential energy gradients? So this is what you get when a portion of the lithosphere is uplifted by some buoyant or flowing material underneath. And this is typically analyzed using isostasy, where we assume that at some depth, the weight of the overlying columns are equal, as expressed in this case here. And then we can compute the gravitational potential energy of each of these two columns. And the difference is an estimate of the force from one column to the other. And you can see this has to do with the height of uplift and the thickness of the lithosphere. And there's a factor of 2 if it's a buoyancy balance, and if it's dynamic support that is due to flow, then you lose the factor of 2. And probably the truth is somewhere in between these kinds of things. So to put an upper bound on these kinds of forces, you can estimate a kilometer of uplift and 150 kilometer thick depth of compensation and densities and so forth, and you get a force which is much smaller than that due to subduction, at most about 5 times 10 to the 12 newtons per meter. And then thirdly, if we look at basal tractions, we can estimate typical convective stresses of about 3 MPa in the convecting mantle, and at most applied over 1,000 kilometers of plate length, to get something of the same order, but probably a bit smaller than these gradients in gravitational potential energy. And I think it's fair to say that there are rifts that are not connected to subduction zones, and therefore are not driven by the strong forces associated with subduction. And so it's empirically true that rifting can occur at driving forces that are less than 10 teranewtons per meter. So sometimes the forces are bigger, but sometimes they're smaller. And this requires some weakening of the lithosphere to explain how the lithosphere can be rifted at those stresses or forces. And it may be high temperatures in the lower crust and the lithosphere. It may be inheritance of suture zones and abandoned faults, or distributed damage that have been in the crust and the lithosphere over cycles of distribution, of deformation. Or it could be a mantle source of magma that is enabling dike injection. And this last point has been deemed important for decades, and it's really where I want to focus the attention today. And it's been, asked of me and of others, is this a which came first, the chicken or the egg, in terms of rifting and magmatism? But I guess my thinking is that it's not a chicken or egg problem. It's a chicken and an egg. These two things don't necessarily happen in sequence, and nor is causality straightforward. So let's just review rifting by slip-on faults. And this is the typical geodynamic scenario that's envisioned. We assume Andersonian faulting strength, and that gives some constant, which is roughly the slope of this strength curve with depth. And then if there's water pressure in the crust and lithosphere, then that will reduce the force for rifting, and the lithospheric thickness squared gives us something like the area of this triangle. And so depending on how thick the lithosphere is, the force that's needed tends to be quite high. If you're looking at 50, 60, 70 kilometer thick lithosphere, then the force is quite large, which maybe subduction can supply. Whereas potentially, rifting is happening in some cases at forces much lower, at about 5 teranewtons per meter. And in the geodynamic modeling literature, of which this is a state-of-the-art example, this is a typically envisioned scenario where you have a strength diagram. This one has 3 layers, but the previous one had 2 layers. And these are roughly Andersonian type friction models and faulting models. And you get these shear localized onto faults, leading to thinning and exudation. And typically these papers, although I can't say I've looked at all of them, they don't mention the stresses or the forces that are required to drive this deformation. But they rather impose the extension in terms of a strain rate or a displacement rate of the boundaries. And whatever force is needed is then supplied. But I mean, they can do an amazing job at modeling localized deformation in some of the structures that are seen in observations. And so that's a remarkable achievement. But when you look at the prime example of a modern rift, what you can see is that magma plays a role all over the place. So here's a map from Corti et al. No, from a Corti review, and based, I think, on Boccoletti's original work. And you can see from bottom to top, whether it's the sort of Wanji faults, which are associated with magma, to eruptive centers, which dot the border faults and the edges of the rift valley, that magmatism is important. And this has been summarized by this Ebinger paper, and a lot of people have riffed on this idea that magma assists rifting at each stage, from the early stage all the way through to the late stage, that magma injection into the lithosphere and crust is a part of the dynamics. But the calculations are much harder to come by in this regard. There are much fewer. And a classic one is due to Roger Buck, where the approach is to really essentially think of this again in terms of a difference in the gravitational potential energy. And so instead of comparing an upraised piece of lithosphere to one that hasn't been upraised, we compare a column of magma to a standard lithosphere of crust, mantle and crust. And the density difference integrated with gravity and height or depth gives this difference in gravitational potential energy. And it's assumed, as an approximation, that the magma density is about equal to the crustal density, and that's less than the mantle density. So there's buoyant magma here in the mantle, and then it's neutrally buoyant in the crust. But to achieve a extension, that magma needs to not go straight through and have the dike close up again, but rather to remain open. And to remain open requires a tectonic force to hold the system, to hold this system open and to hold the magma down, in addition to some deformation to initiate the dike. So this is quantified similarly, and you end up with this blue line, which shows the strength with melt, and conveniently passing right through the region of the forces and thicknesses that are associated with gravitational potential energy driven rifting. So again, not all cases will have forces that are this small, but some do, and therefore it makes sense that this mechanism could explain that. So the Riftomat project, which I mentioned at the beginning, aims to try to build on these simple calculations by developing a geodynamic theory, which is a little bit like the geodynamic models that I showed that Sasha's been involved in, Suzanne's been involved in, and a lot of other people over the past 30 so years have been involved in, where plasticity stands in for brittle fracture. And the models are continuum models of what is in reality discontinuous deformation of fracture and faulting and earthquakes.
You have 10 minutes now, okay?
Thank you. And so we're building on the theory of asthenospheric poro-viscous deformation, which was established by Dan McKenzie in 1984, building, of course, on previous work. And I don't want to go through the PDEs, but I do want to mention that I wrote a book about this, and it's coming out sometime later this year. So keep an eye out for that if you're interested in this subject. But to model rifting, we have to go beyond the poro-viscous theory, because clearly the lithosphere is not a viscous medium. It's elastic, it's brittle, and it can deform viscously over longer timescales by low temperature plasticity. So we need to enrich the theory and the models to capture that. And that's what the Riftomat project is trying to do. And so in that direction, we are working with a viscoelasto-viscoplastic theory. Now, this is a little bit for specialists, but this is taking ideas that have recently been developed in the geodynamics community by Thibaut Duretz and others that seek to use viscoplasticity as a way to regularize plasticity and make it a little bit more amenable to numerical modeling. But this is done in the one-phase flow community. So this is where you don't have any magma present. When you have magma present, then you need to account for the effective pressure. So this is the solid pressure after the liquid pressure has been subtracted off, because the liquid pushes the pores open, it pushes the grains apart, and it weakens the rock. So as the effective pressure goes down, then rocks can approach this failure criterion, which is a frictional or a plastic yield envelope. And when they yield, then they become much weaker. And this should apply both to pseudo faulting, so the kind of shear bands that you see in typical geodynamic models of rifts, as well as to rifting, as well as to diking, where the sides of a dike are pulled open and magma is injected into the space in between, probably with a low effective pressure. And so we enrich the rheological model, or the flow law that I showed in the previous slide, with this viscoelasto-viscoplastic moduli. So this is an effective shear viscosity and effective compaction viscosity. And this is shear deformation and compaction deformation, so dilation or compaction of the rock. And these are inherited elastic stresses. So there's all kinds of thorny mathematical and physical details that there's no time to discuss here, unfortunately, because this is the real meat of the problem, is working the details out. But I want to show you some preliminary results that are very, very new. And again, credit for getting these done to Yuan, who's worked really hard to do what are, I would say, unprecedented calculations, even if they're very preliminary at this stage. So in this case, we've simply got a lithosphere, high viscosity, elastic modulus, and cohesion at a small strain rate. And there's a magma body at the bottom. And we're pulling on this thing, as is typically done, at a fixed strain rate, and there's a free surface. And in this panel, you see the porosity. So you see these channels, which are effectively dikes in the context of this calculation. Of course, they're very approximate, and we can discuss that. And they're rising up through the lithosphere, and they're connecting right about there with what are faults. So you can see strain rates at an angle to gravity, which are faults, and those faults are progressing through, partly because we have no memory in these calculations of previous plastic deformation, although that's something that should probably change. And you can see that they're driven in part by the extension and in part by the liquid overpressure, and that these dark colors indicate a liquid overpressure, so a pressure in the liquid which exceeds that in the solid. And that liquid overpressure leads to a lower yield stress and yielding. And you can see that these relax the stresses in the medium, leading to extension at lower stresses, consistent with the magma-assisted rifting hypothesis of Buck, and that they assist in the divergence of the solid phase, so opening up space. I want to show one more calculation, and maybe actually I'm going to skip this because I think I've run out of time, but this is essentially the same parameters except for a much lower viscosity. So instead of having an elastic lithosphere, we now have a viscous lithosphere. It's not really a lithosphere in that case, but just for comparison, and we can see a slightly different mechanism of propagation of melt upward through the lithosphere. But I'm going to skip over that and just summarize. Magma participates in the mechanics of rifting in essential ways, but this has typically been neglected in previous models, geodynamic models. And simple theories such as that by Roger Buck and students and postdocs, some of which I haven't shown you, indicates that it can explain rifting at low stresses. And what we're working on now and making some progress with is extending this to computational models of two-phase flow geodynamics. So I'll end there, and thanks for your attention.
Excellent, Richard. Very nice results. I'm looking forward to see more of that. There's time for one or two quick questions.
Sorry.
Yes, sorry, I've obviously messed up my registration. This is Kathy Whaler. So I was wondering if you think there's any chance of this kind of numerical approach leading to magma propagating upwards in sills rather than in dikes, which is what seems to be observed quite regularly in the East African Rift and Afar.
Absolutely, I think that is definitely the case. What we did in these preliminary models was assume a constant density difference between the solid and the liquid. So it's, a 500 kilogram per meter cube difference, no matter where the magma comes from and where it ends up. But of course, the lithosphere is stratified in lithology and density. Magma evolves as it ascends, and I think stalling and it cools, and stalling in sills is very likely to be related to these kinds of factors once they're incorporated into models. So I wouldn't say that I know how that works, but I would say that it is going to be related to the factors like lithological stratification of the lithosphere and density evolution of the magma, factors which we haven't investigated quantitatively. I think that's the best I can do in answering that question.
There's one more question by Sarah. Could you ask it, please?
About computation.
Sarah, do you want to ask it yourself?
Sure, I can ask. I actually have to run now, so I don't know. I was just wondering what kind of computational power is needed for the Yuan-Yi calculations that you showed.
So those 2D calculations were done by Yuan on his laptop. It's not an old laptop, but still, it's not a massive amount of power. I'm sure that they could go to much higher resolution and probably without going much slower on a cluster. But really, we're in the development phase and grappling with different formulations for yield stress and so forth. So we're really testing it at fairly low resolution. But thanks for the question.
And there's one last question. Since you can't answer questions in the chat anymore, we have to go through some more questions. Ottmar, could you ask it, please?
Yeah, thanks, Rich. It's very interesting models. I was wondering, when you model your melt pathways, are these really dikes or are these melt rock reaction zones like mechanisms that was proposed to form donites beneath mid-ocean ridges?
In these models, they are definitely plastic failures. So I can say for certain that they're not melt rock reaction because we don't incorporate the physics. I mean, no thermodynamics, no composition, no reactions in these models. These are purely mechanical models, for better or for worse. I mean, that's just where we're starting, of course. So that's not the case, but whether we can actually call them dikes or not is a little bit of a philosophical point, because I mean, for example, with geodynamic models that involve plasticity, are those faults or are they plastic shear zones? It's sort of, yeah, I can't decide that question.
Okay, thanks.
The last question from Suzanne is very short, so let's deal with that.
So Richard, my previous comments were just about the stress levels related to rifting, but for your set of equations, what's the amount of effort that's involved in coding? So if we want to implement this in our codes.
That's a difficult question, I would say, because it depends a lot, I think, on how much experience one has with these equations. I mean, at first glance, they're clearly more complicated than the single phase flow equations. But they're not 100 times more complicated. They're, maybe 10 times or something like that. The problem is that you start coding these things up and you need to really understand what to expect so that you know whether you've coded it correctly and whether your solver is working and so forth. And so it takes quite a lot of careful testing. And I think this is what's made it very, very slow for us. I mean, we've been working on this for 1.5 years now, and step by step, making sure that the additional physics is behaving according to benchmarks and physical models and simpler models and so forth. So I think, it's a lot to expect of a PhD. I wouldn't necessarily take that approach. And I think, it's something that we might discuss in more detail. I hope that we will make some of the software that we're developing open source and potentially collaborate with people who want to work on it. I think if you have a pre-existing code and you want to sort of bolt this on, I'm not going to recommend that. I think that could lead to big headaches. That's why we started from scratch.
I see the last that you raised your hand. Sorry, I was looking at the chat all the time. Could you ask the question quickly, please?
If there's still time. Very nice talk, Richard. Very cool.
Thanks.
Just for if you then think about margin evolution, I guess what you show is that most likely you can break at lower stresses. Is then the margin formation related to magma supply? Would you basically have to keep having dikes shooting in to have it low enough to continue rifting? Yeah. Or do you expect some sort of interaction driving some other faulting?
Yeah, I mean, this is partly about magmatism and partly about evolution of rifts, which is I'm very new to this subject and to this community. So I think that, like Otmar said, once you've got this process started, it is likely to be self-reinforcing because you weaken and then you thin and you produce magma by decompression. And this is a process that has a positive feedback. So I think if magma is available in the early stages, then it's likely to be available throughout. And really the crux of the problem is the early stages, whether you need pre-existence of magma to initiate at low stresses or whether you somehow it initiates and then produces the magma that allows it to proceed to tectonic extension. I hope that we'll have something more to say about that in a couple of years. But it's definitely a long road in building these models. So that's the best I can say right now. Thanks.